Okay, so we had some fun calculating integral rules by looking at derivative rules and then going backwards. Or at least I had fun doing that. Now, this is not the kind of work that I want to be doing every single time for every different function that I know how to take derivatives of. I want a method, and I want to be able to know when I can use it, and I want to know what the steps are that I use every single time. So this technique is called U substitution, and you can find it in the textbook in section 5.5. I highly recommend you be reading the textbook as we work through these lectures. On the integral side, we've got something complicated that we want to integrate. And here I have chosen that very same function that I calculated in the last video. So we should get the same answer. The trick is that we're going to rewrite the integral formula in terms of a new variable. And here I'm going to use the variable u. So in my first step, I want this formula to look like integral of u of x. So my variable u is going to be a function of x. And that means that my function u is also going to have a derivative, u prime of x. That gets shoved under the rug a lot, but it's important for what I'm doing here. So you can think of this as sort of a change of variables. And when I do my change of variables, I also have to keep track of the differential. That's the dx on the end of my integral. So when I write out u of x times u prime of x times dx, that's kind of a lot to write. So the traditional way we throw that under the rug is we say that u of x is just u prime of x times dx is du. You can also think of the u prime of x as the conversion factor. How much of a dx do I need to make up a single du? Well, I need a u prime of x is how much of a dx. That might be a little bit abstract. Let's actually work on this problem. I want to be able to identify what I'm substituting, right? I'm going to be picking some part of my formula out and calling it u. The technique that I like to use, will work most of the time, is that I am trying to find the deepest nested part of my function. So I'm looking for the most complicated part of that function with the most number of parentheses. In this problem, that's going to be the 1 plus x squared that's inside my parentheses here. So keeping the long notation, just to explain what I mean, I'm going to say that u as a function of x is equal to 1 plus x squared. And again, I picked that because it's the deepest set of parentheses that I can see. Once I've selected my u, I also need to calculate the corresponding du. So the formula I use for that is that du is the derivative of u in terms of x times dx. So this formula governs the exchange rate between my differential in x and my differential in u. So what is the derivative of 1 plus x squared? It's 2 times x. So my conversion factor for today, my exchange rate for today, is that a du is worth twice x of a dx. Now, the thing to remember here is that the differential needs to have the same variable as the rest of the function we are integrating. So I know that I've made the correct substitution when all of my x's turn into u's instead. So let's gather those equations from my last two slides. This should say u, so a u is equal to 1 plus x squared, pardon the typo. A du is equal to a 2x times dx. So here's my first formula. This was the integral that I've been asked to solve. And I'm going to rewrite that so I can find all of my pieces inside. So I'm saying this is a 3 times the quantity 1 plus x squared, which is then squared, times the quantity 2 times x dx. Okay, cool. So that 2x dx, that's my du. That 1 plus x squared, squared again, that's a u squared. The 3, well, the 3 just comes along for the ride. Again, I know that I've done the substitution right because every single x has now been turned into a u. It also helps that this is a much simpler integral than what I had before. So this stuff over here, maybe I can multiply that out, do a power rule, but I don't want to. I want to do this. It's so much simpler. So I'm going to integrate what is the integral of 3u squared du. Again, it's an indefinite integral, so I know that I'll have u cubed as my antiderivative plus some constant of integration. And that's pretty much it. Oh, right. This problem was originally posed with the variable x. So if I want a meaningful solution, my answer needs to be in terms of x as well. So my integral step is now super easy. I calculate my integral, I get my u cubed plus c, but I need to convert back into my x coordinates. So I say again that my u is equal to 1 plus x squared. So this must be 1 plus x squared. And that quantity is going to be cubed plus the constant of integration. And hey, that's the same answer that I got on the last video. Isn't that neat? Now, I'm expecting that you probably started to see this material in your previous calculus class. The next video I'm going to do is another one of these formulas, which is really just the calculus version of a derivative formula. And that is going to be integration by parts.